Hi everyone. In today's lesson, I will teach you the basics of celestial navigation, the basic theory of it, so that in the next videos, when I start solving the questions based on this theory, you can have a better understanding of it. Alright, so let's get started. So, in today's video, I will discuss the theory of celestial navigation. So, just the basic theory, good enough for you to understand, doesn't go into all aspects of it, but what is the basis of celestial navigation? So far, you must have understood how do we calculate courses and distance on the surface of the earth. So, here we have the earth where we have a reference circle called the equator, and this reference circle is used to measure the parallels of latitude or other parallels of latitude. So north of equator we go north, and then south of equator we go south as well. So these are parallels of latitude, and then we also have longitudes, right, originating from one pole and going into the other. Now if we have to plot a position of a vessel or a person on a vessel, so what we do is basically find out which is the latitude and longitude this person is situated in, and determine that this is the geographical position of the person or the vessel. So we'll say a person in this case, or we will say he's an observer, because that is the term that I will be using for celestial navigation as well. So when I say a person or an observer, I mean us humans on the surface of the earth, as well as someone who's working on the ship. So a ship's position is also determined by the latitude and longitude, and so is a person. So any position on the earth system is based on the geographical coordinates of latitude and longitude, right? That is the coastal navigation system, or the basis of coastal navigation system, and this is the basis of our plain sailing and Mercator sailing, or composite great circle sailing, or great circle sailing as well. All right, so what happens in celestial navigation? So basically celestial navigation is used when you cannot use any of the geographical coordinate system. So you could say that if your GPS fails and you don't have access to your lat and long, or your latitude and longitude, how would you go about plotting the position of a ship, or even a user or an observer on the surface of the earth? So to do so, what we then do is we use a celestial navigation system. Now what the celestial navigation system assumes is that around the earth or surrounding the earth is a vast sphere of unlimited radius, the radius of which is not known. You cannot measure the radius of this vast sphere, and this is called the celestial sphere. So this celestial sphere does not have a radius. All right, and this is a vast infinite, we call it an infinite radius, a radius of which cannot be measured, and that surrounds the earth sphere. And what we then do is we project what we have on earth onto the celestial sphere. For example, the equator is then projected onto the celestial sphere and called the equinoctial. The latitudes or the longitudes are also projected onto the celestial sphere. So the latitudes are then called declination circles, and the longitudes are called hour angles. But the hour angles are not measured as respect to or similar to the longitudes. The longitudes are measured with reference to the 000 degrees prime meridian, right? Now we also have something called a celestial meridian, and we have celestial Greenwich meridian and celestial prime meridian as well, we call them. But this is not the basis of the position fixing system in the celestial sphere. So what do we do is we project the position of the observer onto the celestial sphere, and we call this observer's zenith. So when the position of the observer is projected from the earth to the celestial sphere, we call the observer's zenith, and then we measure the position of the observer in the celestial sphere with respect to a celestial body. We can call it a sun or a moon or a star or a planet. And how we do that is we do that by measuring the angular distance. Now, what is angular distance? I will explain soon. So a position of an observer is calculated with respect to the angular distance it maintains from the celestial body. Now, if I know the position of the celestial body, and the position of the celestial body is known by its declination, which is very similar to latitude, and the hour angle. So instead of the longitude, we have hour angle. Now, what is hour angle? Hour angle is the angle that a celestial body makes with respect to another body. So that could be a celestial Greenwich meridian. And when I say celestial Greenwich meridian, I mean the Greenwich meridian projected onto the celestial sphere. So when it is with respect to the celestial Greenwich meridian, we call it GHA. The angle that the celestial body makes with the observer is called the LHA. Something that we have with the first, or the angle that they subtend with the first point of Aries, and I'll explain all these terms as we go along, or we proceed in the theory of celestial navigation. So we can have SHA or sidereal hour angle. So these are angles that you measure with respect to another entity. So if I know the position of the celestial body in the celestial sphere, then I can measure the angular distance that it has with the observer. And when I say angular distance, this is how I mean. So in case you were not getting what I'm saying because of my pronunciation or my accent, the angular distance is different from normal distance. So normal distances we measure either in terms of length, isn't it? So centimeters, meters, kilometers, or miles, nautical miles. Angular distance is measured in terms of angles subtended with respect to two entities, let's say entities, right? So an angle has to be with respect to something. So let's say there is a sun here, as you see, and then I subtend my prime meridian here and call it the Greenwich meridian, and then the angle between the celestial body, the celestial Greenwich meridian, and the observer can be measured to find the position of the observer. When I find the position of the observer on the celestial sphere, I just project the position back to the surface of the earth and denote it in terms of latitude and longitude. So I can use the celestial body to find the position of the observer with respect to the celestial coordinate system, and then project the position of the observer back to the surface of the earth and denote the position in terms of latitude and longitude. So the whole system of celestial coordinate system is based on what we call is the rational horizon diagram. Now we also call this diagram the PZX triangle. Now what is the basis of this PZX triangle is that we draw the celestial sphere. Now remember, this is a sphere of infinite radius, and then I draw a vertical line and a horizontal line. I'll tell you what all these means. Now I will put the letters N, S, W and E. Now these are only directions. It refers to the north, the west, the south and the east. These are not poles. This north is not the north pole or the south pole. These are just directions. Remember, the celestial sphere is a sphere of infinite radius. You cannot measure it. So the directions here just refer to the directions. You cannot say that N is 90 degrees away from the center of the circle, just like we do for a Earth. We cannot say that for a celestial system. Alright, so these north, south, west are just directions. When we put Z or the observer in the center of the celestial sphere. So what we are doing here is basically visualizing, looking at the celestial sphere, but from the top. We call it the bird's eye view. So we are basically looking at the head of the observer. We are looking at the observer from the top. That's the view we have taken. Alright, then if what we do is the observer always stays in the center of the rational horizon diagram. Now, if the observer is in north latitude, we project the north pole here. This is the north pole. So P is the Earth's north pole projected onto the celestial sphere. And we draw the equinoctial or the celestial equator south of the observer. And we call it Q. Q stands for the equinoctial or the celestial equator. So what happens is if WQE becomes the equinoctial. So WQE is the celestial equator or the equinoctial. And by putting the observer north of the equator, I am trying to show that the observer is in north latitude. I'll also show you what happens when it's in south latitude. Alright. So NP equals ZQ always. And this equals to the latitude of the observer. Alright. And then we have the celestial body which marks a journey from east to west. So the sun of course rises on the east, most of the bodies rises on the east and they set on the west. Alright, so the sun rises on the east. I'm taking the example of a sun, but we can talk about any celestial body. And then it traces a path from east to west with respect to the observer. When the celestial body is on the meridian of the observer, when it is at the position x dash, so that means if I just draw a straight line or a vertical line and I call this Z, this is the observer, and the celestial body is in the same meridian as the observer. So either it is here or it is here depending on the latitude and the declination of the observer and the celestial body. So it could be north of the observer or the south of the observer, and they are both in one line, right? So in this case, let's say, let me get rid of one of these x's. So in this case, let's say I draw Q here. Remember, Q is the celestial equator and I call it equinoctial. So in this case, the declination of the celestial body is north because the celestial body is north of the equator, and the latitude of the observer is also north because the observer is also north of the equator. But the celestial body is bearing south of the observer. Now they are all in one meridian, they are all sharing the same meridian. Basically the observer and the celestial body is sharing the same meridian. This is an example of a meridian passage, when the observer and the celestial body shares the same meridian. Now with the case of the sun, it happens normally at noon or close to the noon 12 o'clock time. This is the meridian passage time. This case could also be where the observer is south of the equator, so this becomes a south latitude, and the celestial body is north of the equator, so declination is north. So in this case, the sun is bearing north of the observer. But again, this is a case of meridian passage, when the celestial body and the observer share the same meridian, and the observer is exactly on the observer's meridian. Sorry, the celestial body is exactly on the observer's meridian. It could be north of the observer or south of the observer, doesn't matter, but they are on the same meridian. This situation is called the meridian passage. The other situation is if a body is at any point of time, let's say body is here. When I say body, I mean celestial body, I mean a sun or a moon or a star. And you're trying to measure an angle or distance between the observer, the celestial body, and the pole in this case, or the Earth's pole in this case, right? This angle is called the azimuth, and we do that in compass error questions. We measure the bearing of the celestial body from the observer. This can be done at any point of the observer's journey, from here to here to here, any position. We can take compass error at any point of time. If we do it exactly when it is on the rational horizon, when we do it exactly in the rational horizon, so when x is here or x is here, when it is rising or setting, the body is exactly rising or setting, and we are calculating the bearing, we call it the amplitude method. When we are trying to determine the angle that the observer and the celestial body is making with respect to the rational horizon, this is called the amplitude method of calculating compass error. All right, this distance zx is the distance we call is zenith distance. This is the angular distance between the celestial body and the observer. Now I keep mentioning angular distance. What does angular distance mean? Let's see with an example here. So let's draw another diagram. So I'll draw a rational horizon diagram, draw a horizontal circle and a vertical line, call it north, south, west, east. Put the observer in the center of the rational horizon. Maybe make it a north latitude again. So if I have to make it a south latitude, I will show you what I mean later on. This is the North Pole. All right, now if the observer is or celestial body is here, and you are measuring this distance here, zx is the zenith distance. We call it the zenith distance, and this is an angular distance. Now what does this angular distance mean? Let's understand this. So remember, although we cannot measure the radius of a celestial sphere, we say that the observer is always maintaining an angular distance of 90 degrees from the rational horizon. All these distances are 90 degrees from the rational horizon. And this is 90 degrees of angular distance. What does the angular distance 90 degrees mean? Right? That means that if I get rid of all the rest of it, so that you guys don't get confused, I'll get rid of this and I'll show you only with one example, and you will get it with one example only. What do I mean by angular distance? So angular distance means, let's say if z is 90 degrees in this case, and I draw a line perpendicular to this means this distance is 90 degrees. It's an angular distance. So what is the distance that the plane passing through the observer is making with the rational horizon at any point of time is 90 degrees of angular distance. So to find zx, we always say, now if this is right, so from z and to, let's say, we call it, we can't, I don't want to give it a letter, from Z to this point is 90 degrees. Yes. Now how far a body rises above an horizon, so this is the sun and this is the horizon, how far the body rises from the horizon is called the body's altitude, right? So this distance then becomes altitude of a body, or true altitude of a body, because this, the black line represents the horizon, and how far the body rises above the horizon is the true altitude. So zenith distance, which is this distance here, Zx, is always 90 degrees minus true altitude. So you can see why, because from x to the horizon is the altitude of the body, how far it has risen from the horizon. From z to the rational horizon is 90 degrees, so Zx is 90 minus true altitude. So these are all the parameters and formulas that we'll be using in celestial navigation calculations. So before I get into that, I thought I will give you a quick background of what is celestial navigation and what is the basis of it. Now remember, celestial navigation is a vast topic, and that's why I have made hundreds of videos on it, and it's there on my channel. Please watch it to increase your knowledge. This was just a basic understanding of the celestial navigation system and the rational horizon diagram. It goes much deeper into it. Make sure to watch the other videos in my channel if you're interested. Otherwise, this basic knowledge is good enough for you to start solving the questions related to meridian passage, compass error, and when I do the intercept questions, I will explain a little bit about the theory there as well. Thank you for watching, and I'll see you soon with my next video on meridian passage.